Hey, good morning, everybody. Looks like there's still a few more people joining, but we're going to go ahead and get started. My name is Pepper Hastings, and with Innovative IBM, fresh out of a dermatology procedure. And so that's what the mask is all about. Today, our 40-minute webinar is power measurement in your modern facility. And we thank you for taking the time to join us here. Our presenter today is Mark Imordino. He is a field training engineer with WAGO, and a proud North Carolinian and a alumni of North Carolina State. So Mark, turn it over to you. You got it from here.
All righty, Pepper. Thank you so much. All right, good morning, everyone. Again, Mark Imordino, WAGO Corporation. So we're going to take a look at power measurement in different applications, facilities, and things of that nature, how it impacts the modern facilities and the things that you need to consider. So figure we got 40 minutes here, might as well just jump right in and get started on this. So just a quick overview of the agenda here and what we're going to be discussing. We're going to look at the different power measurement fundamentals, look at some applications, industries that are impacted by this, look at some basic terminology with regards to the power measurement fundamentals, power factor, harmonics, active power, reactive power, things of that nature. We'll talk a little bit about measurement devices to give you a better understanding of how all this is accomplished. And then we'll look at some other devices with regards to monitoring and measurement from the field devices. So from the measurement device to the PLCs or other devices that can measure these signals from things like current transformers and Rogowski coils. Look at some of the software options that we offer with WAGO and how that's incorporated with our PLC line and other devices. And then we'll do a quick review of and overview of the cloud connectivity and how that's important or potentially can be important to you. Maybe not today, but definitely in the future. So it should be something that you're looking into, investigating, and coming up with possible solutions, because it will be something that will be discussed later on, I guarantee it. So when we talk about power measurement, the big thing here is, what we're trying to do is collect data about our energy consumption and use that data to analyze what we're doing, our efficiencies and inefficiencies within our facilities. So commercial sectors, which includes things like offices, hospitals, schools, stores, things of that nature. Primarily their energy is for things like HVAC, lighting, heating, things of that nature. So 60% of their energy consumption is used for lighting. And the building sector uses approximately 66% of the electrical energy in the United States. So by using intelligent and accurate measurement and control of this equipment and the control of HVAC, lighting, elevators, it makes it possible to significantly reduce the electricity consumption of the building systems themselves. On the industrial sector side, you have where approximately 26.7% of the U.S. electricity consumption comes from these sectors. The top six being petroleum, steel, aluminum, chemical, paper, and cement. So a lot of this is the motor-driven equipment that accounts for 64% of the electricity consumed in the U.S. industrial sector. And within the nation's most energy-intensive industries, motor systems consumption is approximately 290 billion kilowatt hours per year. So there's a lot there to take in to analyze. So with these individual industries, improvements to motor systems could yield dramatic energy and cost savings. The keys to these savings could be applying energy efficient equipment or implementing sound energy management practices. And the only way you're going to be able to do that, of course, is to analyze how the systems are running, do a comprehensive data collection of the systems during normal production hours, abnormal production hours, startup, stops, and things of that nature. So with energy prices, they keep going up. Businesses, every business, whether it's industrial, commercial, doesn't matter. They're all looking to, make innovative changes for efficient, affordable, and clean energy. Okay. So Some of the application examples we look at, looking at power measurement data can be, optimized to supply power to drive or machine systems, resulting in lower energy costs. So maintenance can be scheduled if a system begins to require power above and beyond its normal operation. So again, when we're talking about machine power here and looking at the power measurement systems that are available. So, different things like automotive with stamping operations, assembly and weld cells, energy management, substations monitoring, genset monitoring, material handling for conveyors, stackers, sorters, packaging machine fillers, case packers, wrappers, petroleum industry, of course, oil drilling platforms, generators, pump monitoring, and then of course various process controls for induction furnaces and heaters, for metals and plastics and batching systems. So again, the big thing here is there's a lot of different things out there, a lot of different industries that are implementing and using these types of power measurement systems to analyze what they're doing today. Another is the motor current measurement data, which can be used to detect instant or cumulative loading to protect an installation from potential failure. So you're constantly monitoring, looking at these systems, overload conditions that can be easily detected, excuse me, initiating a system shutdown to prevent costly damage to the equipment. So, if you see binding or anything like that on the load side, of course, you're going to see an increase on your energy usage on your motor control circuits. So when we look at things like general load monitoring and phase balancing with MCCs, batch and mixing systems, so batch overloads, stamping. So like if you're stamping, obviously you get over tonnage conditions where something's not quite as binding potentially in there. Hydraulic pump systems, so detect pump failures or cavitating pumps. Indexing tables, preventing damage to gearboxes and drive shafts and so forth. So again, it's not industry specific, it's across many industries, across many applications. Another one, we often think right out of the gate, well, because of our backgrounds and what industries we're in, it's always industrial applications. Well, even your facilities, you have your production area, and then of course you have your office area, maybe where design engineers and other people are housed. So even with those, we need to look at building automation and how we can use power measurement to monitor transformer loads for those lighting circuits, HVAC, for loading and balancing of transmission lines to the building itself. So we use this data to track power usage during daylight or seasonal operation to trim our usage cost, right? So just about anything in a facility, and it can be all kinds of things that we can do with that power measurement data. We could have an automated blind system. The lighting controls can be automated, obviously the HVAC as well, but all these things can be looked at based on the power measurement data we'll pull in and we can analyze. So let's just get into a couple of the basics when we talk about power measurement and what we're trying to accomplish. You have what's called active, true, or real power. And this is the power which is actually consumed or utilized within the AC circuit. And it's typically measured in kilowatts or megawatts. And what it boils down to is your true power is basically equal to your voltage and current in phase with the voltage, your voltage times current in phase with the voltage. So that's what we're analyzing when we look at active power. Another thing that we would look at is reactive power. And this is the power which flows back and forth, and it means so that it moves in both directions in the circuit and it reacts upon itself. So basically this power is required by inductive loads. It's not used to complete the actual work, but is required to maintain proper supply voltage and ultimately deliver the appropriate active power, which we just talked about. So reactive power is measuring instantaneous power actually be negative because the voltage and current waves are not in sync with the active power coming in, okay? So because this can flow back from or excuse me, flow back to the power grid. It increases the resistance of supply, and it can add additional load to the transmission lines and additional cost as well. We'll look at that as well in just a moment. All right, so with another term that we use a lot of times when we're looking at power measurement and what needs to be analyzed is apparent power. And apparent power is the combination of active or true power that we talked about earlier and reactive power. So you can see everybody gets this illustration here pretty easily. Our little glass of beer here. So we have our active power, the usable power, if you will, or used power, and then our reactive power. Okay, and that total is our apparent power. And we use these because we do another calculation with this information. So the apparent power is essentially the product of the root mean square value of the voltage and the current. And it's measured in volt amperes, kilovolt amperes, and megavolt amperes. But so again, these are all just the different things we have to consider when we're looking at power measurement and analyzing the data and collecting this information. So another term is power factor. And this one we've probably all somewhat heard of. This is, we've heard it mentioned like in power supplies, switch mode power supplies, for example. And this is power factor is basically the ratio between the active power and the apparent power. Okay, so those terms we talked about earlier, and it's the ratio between the two. They typically fall somewhere between 0 and 1, which 0 is the worst, 1 being ideal. It's a good indicator of the quality of the power that you have or how it's being utilized. So the significance of this is that the utility companies supply customers with volt amperes, which is your apparent power, but then they bill them for the active power, watts. Okay, so when you look at this, if your power factor falls below that 100% requirement, a utility company has to generate more than the minimum volt amperes necessary to supply the active power to the system. And this increases generation and transmission cost. So we'll look at a cost analysis in just a moment. But basically what it boils down to is, your good power factor is considered to be somewhere between 90 and 95, obviously. So 0.9 to 0.95. 1 would be ideal, would be perfect, but it doesn't always happen. And so what happens is if you fall below those, or the worse that number gets, the utility companies are going to charge additional costs to the customers who have a power factor below that range, below that 90%, if you will, or that 0.9. And since all of these factors aid in the measurement of energy usage, collecting and tracking that information helps you monitor your energy cost and can, down the road, can make your system more cost effective, your operation more cost effective, and reduce your overall, cost of doing business. So again, that's, one of the big reasons why we look at this kind of stuff is, how can we save money, find our efficiencies or inefficiencies, and fix them. All right, so when we talk about power measurement, as I said, here's a quick example. You've got a utility bill that's about $50,000 per month. Your power factor drops to 0.84 during startup, your peak demand. So the company has to be able to handle this demand. So of course they have to charge for additional power usage during that time. And so the utility bill could then be increased by $62,500 a month at 25%. So again, because that penalty that you have to pay and the difference in your standard utility bill and your power factor drop as far as your efficiency, then it's going to cost you money. So again, over time, that's a lot of money. It starts to add up, right? So another thing to consider, not just power factor and everything, but also harmonics. These are distortions in the wave pattern that are another contributor to the degradation of power factor. The sources of harmonics can be things like VFDs, welders, fluorescent lighting, computers, television, things like that. So all of these devices can cause harmonics within our system and our power. So what is a harmonic? Well, basically it's a excuse me, are currents or voltages with frequencies that are an integer multiple of the fundamental power frequency that's coming into your facility. So obviously, typically what we're looking at is, let's say 60 hertz in the US. So when you have harmonics riding on top of that, you'll see these, like a third harmonic would be 180 hertz, a second would be 120 hertz. And what this happens is it causes distortion across your power system. And those distortions can cause things like current overloads, motor, relay, and coil overheating, breakers and fuses failing, um, lights may flicker. So all of this can lead to premature component failures, efficiency losses, operational breakdowns. And anytime that happens, now you're not just talking about cost for power, now you're talking about cost in your manufacturing. So obviously these are things that need to be considered. So we've talked about all these issues about the things and why people want to look at this stuff. Let's look at how we do some of it. Okay. So one of the things we use for this power measurement is CTs, or current transformers. They come in many shapes and sizes and are designed for a wide variety of current measuring applications. CTs are instrumental transformers that are, instrument transformers, that are used to supply a reduced value of the current to meters, protective relays, and other instruments like PLCs and IO cards. They provide isolation from the high voltage on the primary side and step it down to a magnitude that is measured on the current to a value on the secondary side that can be handled safely by the instruments and the maintenance people. And these secondary outputs output currents are normally either 0 to 1 or 0 to 5 amps on the range for the device. And you have different types: donut, split core, bar type. You've probably all seen these, but it's a type where you have the main line, your primary current, going through the CT, so we can measure this information to an amp meter or a PLC IO card. Another device that we use is called a Rogowski coil, and the Rogowski coils operate on the same principle or similar principles to a conventional iron core CT. The difference is that the Rogowski coil windings are wound over a non-magnetic air core instead of over an iron core. As a result, the Rogowski coils are linear, since there's an air core, and they cannot saturate. Of course, one of the things, it's a hazard with the CTs is when they get into a saturation condition. So with that, the mutual coupling between the primary conductor and the secondary winding in Rogowski coil is much smaller than CT. So a resulting signal that we're getting from the Rogowski coil is much smaller, and the Rogowski coil output is much smaller, so it cannot drive current through low resistance burden like CTs are able to drive. So that's kind of, you got to understand, it's a similar technology, but it's a lower current rating. So again, that's a benefit, but it also can be a drawback. So you have to make sure that the Rogowski coils, the signals go to microprocessor based devices or devices specifically designed for Rogowski coils. Okay. So these devices, of course, measure the voltage across the Rogowski coil secondary output terminals. And the nice thing about the Rogowski coils is where CTs, especially if they're solid core, if you install a CT on the front end, great. If you have to do it in the field, a lot of, once the system's up and running, then typically you want to try to use some kind of split core, because the solid core, of course, you would have to remove the conductors, install the CT, and then reinstall the conductor again. You're talking about large conductors, high voltage, high current capacity. With the Rogowski coils, it plugs right into this base module here. So you can unplug it, wrap it around the main conductor, plug it back in, and you're off and running. Something like a split core, but much easier to handle. The base unit in blue there usually would fit in the palm of your hand. So they're really small. So looking at this from an application standpoint, you have here the Rogowski coils or CTs with your main line going through. We have some of our power tap terminal blocks with voltage taps on here. And all of these signals go through various types of terminal blocks. Wago has very specific terminal blocks for CTs, for CT disconnects. So those are important. I'll go into too much of that, but just keep that in mind, our 2700 series disconnect blocks. And then this signal is passed over to, could be one of our three-phase power measurement modules. So the line voltage comes in on one side, your CT measurement comes in on the other, and then we can use this data and analyze this information. And we'll get into how we do that in just a moment. But then, of course, once we get this information, we collect this data, now we can push it up to the cloud, all right? And then use that, anyone can use that data, analyze that data. Of course, the benefit of the cloud. So we have here the power measurement modules, 3 different versions, 3-phase 480 and 690 volt, various sensor types. We have them 1 amp to 5 amp CTs, as well as Rogowski coil versions as well. So again, broad offering here just on the IO modules. We'll get into other things. Of course, these work with our PFC 100 and 200, and as well as all of our IO coupler modules and other devices in the field. But primarily, this is our big focus right now, is our PFC 100 and 200 controllers. We do offer, of course, measuring devices, so split core CTs, solid core CTs, different pluggable versions with our PicoMax, Rogowski coils, voltage taps. They're compatible with, of course, all of our IO cards and other devices as well. Yeah, not going to get into the nuts and bolts of this, kind of constrained on time here, but the thing is, we do supply the sensors as well as, all the way across the entire application. With our power management system, you can come in here and you can configure, you can monitor using this 3-phase power measurement. This is just a software utility where you can look at all 3 phases. You can analyze, looking at the data, effective power, reactive power, apparent power, power factor, all of that as a whole. And then you can look at the individual phases as well. Okay. Another thing that we have in our offering is signal conditioners for CT measurement. So sometimes you'll have a system where I can't directly input a CT into the IO device, maybe a legacy system, whatever it can be, whatever it may be. So we do have signal conditioners that have built-in CTs that you can bring in your line voltage through here, get a measurement for the CT measurement for the current, and then we can change that output into a 0 to 5, 0 to 10, 0 to 20, 4 to 20, etc. So, and more different types. So we do have different signal conditioning modules for CTs. We also have them for Rogowski coils. So again, you can use these Rogowski coils just as an input into the device, and then change it to a voltage or current measurement as a direct input into your IO card and system. Okay. We also have what are known as 3-phase power measurement modules. These are individual modules independent of the IO system. And what this allows us to do is the same thing we just talked about, where we can bring our voltage and current measurement into the device, and then we can transmit that via Modbus RTU. Okay. And so you just have a RJ45 connection on here for Modbus RTU. And it allows us to look at current, voltage, power, energy, frequency, harmonics, power factors, phase angle, rotary field. All of that information can be analyzed within these devices. Okay. These work with CTs. You'll see there's versions that the 1 amp and the 5 amp are for CTs, and then the Rogowski coil version. You can pull this data in, as I mentioned, and then send it out over a field bus connection. You can also log it into a micro SD card as well. Another thing is we have this interface software. So if you wanted to, you could, just like you saw before with the 3-phase power measurement modules, you can also use this for these power management modules. And again, measuring all the things we talked about before, again, sending it over 485, Modbus RTU through the connections, or data logging it to the micro SD cards. So here you can see an application example. You'd have the power measurement module here connected to the serial 485 port on the front. This is Modbus RTU, so we could plug this into the PLC here. We can get this information again coming, or this data coming in from measurement values from our voltage taps and our CTs into this device, and then transmit all the data we talked about, power factor, rotary fields, all that stuff over to the PLC via Modbus RTU. And of course, then this device could act as a gateway to an Ethernet based system, right? Could be to the cloud, could be to other devices on Ethernet, whatever the case may be, right? We also, and I'll get into this in just a moment, we also have these pre-written function blocks that we can pull in within our programming tool. So you don't have to be the programming wizard. We've done all the legwork for you on that. And here you can see some examples of the power measurement libraries. We have several variations on these, whether it's for the compact module, the 3-phase power measurement module, or for the like a 494, which is our 3-phase power module that goes within the IO system. So these are pre-written function blocks. You just pull the library in, call the function block, point it to the appropriate tags, and then you can pull the data. So it's that easy. And just to show you real quick, I don't want to spend a lot of time on this, but you can see this is an actual running application. Here's one of the function blocks I called here for one of our 494 cards. And really, it's just a matter of going into the library manager and then pulling up this library. And if I wanted to, I could come in here and just, if I wasn't sure, then one of the nice features about this, just so you know, is if I didn't know, I could type in just, well, I know it's a 494 card, and then I could find the library that's associated with that card. Okay. So again, a very easy application to set up. Pre-written library files, function blocks, functions, and things of that nature, data types, all of that's built in, as well as, I just wanted to show you this real quick as well. You can build your own visualizations. So these visualizations can do things like you can configure and you can monitor. So you can see this is a recreation of another screen, but now we can monitor this and we can actually make these web pages as well. So I can configure the module through here. I can look at the data and the values, and then I can review this as a web page. Let's go to PowerPoint. Okay. All right. Also, we have application notes. So we have lots of different ways to do these things with our power measurement modules, whether it's the IO system or the independent modules, whatever. There's plenty of application notes out there. Please go out there and check these out. Lots of information in there, how-tos and stuff like that. So again, it's not just a matter of you having to figure it out. We do a lot of write-ups like this, these application notes, so it's easier for you to put it all together. Now, the last piece of this puzzle, we talked about going from sensor to the cloud, is, of course, how do we get this to the cloud? And of course, when we talk about that, we're talking about Industrial 4.0 or IIoT. So basically, you have the industrial Internet of Things is the next wave, the latest wave, actually, of innovation impacting the systems that we design and how we design them, okay? So the strength of the IIoT is that everything down to the end device, sensors, actuators, controls, whatever, can be accessed using this internet infrastructure. We can send this data, all that information up to the cloud, and then do this comprehensive data analysis for all kinds of systems and reasons. But we're talking about power measurement. We talked about efficiency and things of that nature with our power systems. So basically, the philosophy here is that smart machines are better than us at accurately collecting, capturing, and communicating this data. So we can take all this data, store it in the cloud, and then come back and use it. And then it's better just to have the PLCs and these automated systems do it for us instead of us manually collecting it from time to time. So the data can be used to pick up on inefficiencies and problems sooner, saving you time and money, and supporting your business intelligence efforts. It can also enhance your quality control, sustainable and green practices, supply chain traceability, and overall supply chain efficiency with your system. So, that's the core thought process of the IIoT. So smart factories today, their goal is to bridge the gap between OT and IT, OT being operational technology, IT being information technology. And, you've got your departments, your engineers, maintenance, and manufacturing operations, which are looking at PLCs and SCADA, right? Your information technology, these guys are, all about IT management, accounting, procurement, and they're using things like ERP systems, web services, mobile apps, and the IT cloud information. So again, how do you bridge that gap? You have a system that can bring the two together, that can do both functions. And that's what really one of our biggest strengths is with the WAGO system. Okay. So when we look at the WAGO system, you can see here, we've got some just standard, let's say, Ethernet controllers, could be Modbus, TCP, Ethernet IP, whatever the case may be. And what we can do is we can collect this data, push it into our PFC 200s and 100s, and then these devices can send this information to the cloud services. Those cloud services could be AWS, Microsoft, Sparkplug, IBM Bluemix, WAGO Cloud, SAP. All of these are supported with the WAGO platform. Okay. And these devices are also Linux-based systems. So we can go a step beyond just using these to push the information. We can use what's called Docker. And Docker is a system within Linux that allows us to load what's called containers. I won't get into the weeds too much, but bottom line, it allows us to run applications in parallel with our code. So things like Python, Grafana, Node-RED, Ubuntu, InfluxDB for collecting data, your database information, AWS Greengrass, Node JavaScript, all of this can actually run within these controllers parallel to the eCockpit program, your machine code. So we can use these to collect data in different ways, push the data out in different ways as well. We also have edge computers and edge controllers, and their primary focus is to maybe disconnect here and everything flows through them. And then we would run these Docker containers on these edge computers and controllers. Again, they're Linux based, and offload that from our standard PLCs to these devices, right? And when we do that, that allows us to transmit this data to cloud services, do all this data analysis. And you can see, again, just with the WAGO system, we can provide you the sensors, the terminal blocks, the IO, the PLCs, and then connecting to the cloud services. So it's basically an MQTT platform connecting to clouds that can act as a gateway between systems, an edge computer and control system. You could even have this going to like a serial bus system, like Profi or CANopen or Modbus, and then sending it out over Ethernet. So then it can act as a gateway, maybe between some old legacy products that you have out there, and you're trying to combine the systems together. Okay. Another nice feature as well with the new PFC 200s and 100s is that we can connect multiple cloud services at one time. So you can have two cloud services. You can push the data to AWS and to Microsoft at the same time. So it's a huge benefit depending upon who's using the data, what platform they want to use, who's collecting it. It could be you're going to have an organization that may be based in Dallas, but they have offices all over North America. So they need to pull this information as well and be able to look at it. That's why you push it to the cloud. Okay. So this is the, power measurement systems, kind of the overview about why we do it, how we do it, and the process and how WAGO supports that. We have a great support team. So if you ever try to use our systems and you're like, I'm not really sure, can't get this thing to work, I can't get it to connect to the cloud, please contact our FAEs, which are local, and then our tech support group that is in-house at our corporate location. They'll be happy to help you. There's all kinds of things we can send you, application notes, information. The FAEs, of course, are local and they can come on site as well. And we also do on-site training. I do a lot of the on-site training. So if you ever have a need where you're trying to use a system and for a WAGO system, whether it's writing the code, designing system, whatever, I can help you out with that as well. So again, showing you from sensor to cloud, how to make these power measurement systems work, how they work, and the different, technologies involved and the terms that you need to understand to do this. All right, so that's all I have with regards to the information we're going to present today. I guess we have a little Q&A session perhaps here, Pepper.
Yeah, Mark, thank you for the concise and informative presentation.